Hello everyone, I'm Jake, and this is Structural Data Analysis Report. So, we are tasked to evaluate the failure probability of a building's structural components, such as beams, columns, over the next 2 years. The failure of the structure could be caused by earthquakes, material fatigues, or extreme wind loads. In this case, we will try to determine the failure for each month. According to the date, we have the starting period of January 1, 2022 until the end of period of December 31, 2023. This is equivalent to 2 years. For a year, we have at least 12 months to complete a 1 year. For 2 years, we gather 24 months to our data. Overall, probability per month will be 4 months as we assume, which leads to 16.67% according to the graph. Therefore, each month can have a 16.67% chances of failure. This percentage reflects the chances that a component will fail any given month.
My name is Vhacshean Belongilot. For continuation, according to the recent data, the probability of failure increasing significantly over time, particularly as the observation period extends beyond a single month. By applying a failure rate of 16.67% per month, the likelihood of failure accumulates. For instance, in just 4 months, the chances of experiencing a failure rise decisively. Over a more extended period, such as 12 or 24 months, the possibility of failure grows steadily. Each additional month adds new window or potential failure, increasing not only the chance of at least one failure occurring, but also the possibility of multiple failures. The data clearly demonstrates that as more months are observed, the risk compounds, highlighting the need for ongoing monitoring and proactive maintenance in areas where failure prevention is critical.
Hi everyone, I'm Jerold Manuel, and for critical and reducing risk of failure, we have here on engineering and maintenance. So as building age, the risk of structural failure increases. To mitigate these, engineers and building managers must take proactive measures. Key components like beams and columns, which are vulnerable to earthquakes, wind loads, and material fatigue. It should be regularly inspected and reinforced. As for analyzing historical data and using probability modeling helps us prioritize at-risk components for targeted interventions. Strategies includes reinforcing vulnerable parts, upgrading materials, and maintaining a consistent inspection schedule to detect early signs of deterioration. Taking this preventive action reduces the likelihood of failure, extending the building lifespan and ensuring safety.
In this task, we analyze the failure probability of a system based on 3 key factors: temperature, traffic load, and material fatigue. We define high and low threshold for each variable, enabling us to categorize data points. Specifically, we assume the following threshold. Temperature above 65 degrees Celsius are categorized as high. Traffic load exceeding 50,000 units are categorized as high. Material fatigue above 0.8 is categorized as high. For each data point, we created new columns to assess whether the temperature, traffic load, and fatigues values were classified as high or low. In this context, 1 represents as high condition, meaning the variable exceeding the defined threshold. 0 represents a low condition, meaning the variable does not meet the threshold. If the temperature greater than 65 degrees Celsius, we assign 1 to indicate that it is high. Otherwise, assign for 0 for low. If the traffic load is greater than 50,000, we assign 1 for otherwise 0 for low. Similarly, if the material fatigue exceeds 0.8, we assign for 1 for high or 0 for low. We then calculated the overall failure probability using a union formula that combines these individual probabilities. This formula accounts for the fact that multiple factors can contribute to a failure simultaneously.
So our next step, we use the overall failure probability to calculate the binomial probabilities for different time periods. We wanted to find out the probability of observing exactly one failure over 1, 2, 3, and 4 months. To do this, we use the binom.dist function in Excel. The formula calculates the probability of exactly k failures in n months, where k is equal to 1, that is 1 failure, and n ranges from 1 to 4 months. Finally, we displayed the results in a table and generated graphs to visualize the relationship between the overall failure probability and the binomial probabilities for different time frames. These graphs help us illustrate how the likelihood of system failure changes over time based on the failure probabilities calculated from environmental and operational factors. In summary, 1 stands for a high-risk condition, while 0 represents low-risk condition, with each contributing to overall probability of failure. This calculation allows us to predict how the system might fail over time and under different conditions.